It is common knowledge that the longer one waits to examine the scene of crime, the less likely is one to gather the useful information about what really happened. By the same token, one would have to comb up a wider area in search of criminal. In a similar way, one may expect the usefulness of an observation in discrete spacetime to be partly determined by the temporal distance that the information must travel between the observed system and the observer. This is called the distance of observation. The distance of observation is easy to define if S and O are single element and information I involved in observation is a single chain from S to O. In this case, the distance is just a length of the chain. Such a chain is analogous to a whirl line in relativity, and the distance of observation is analogous to the proper time along the whirl line. An interesting contrast between discrete case and continuum case is that there is the shortest possible distance of observation in discrete space-time when I consists of a single relation. For obvious reason, we call this situation direct observation. In continuum space-time, however, direct observation is impossible. This is because of a mathematical property called intrapolative property, which is satisfied by real number system and the rational number system. The intrapolative property says that between any distinct pair of real number exists a third real number. The easiest way to find such a number is to simply take average of the original two numbers. This contrast illustrates how moving to a simpler structural paradigm can actually introduce new structural possibilities. The contrast between direct and indirect causation is actually important for modeling matter under strong form of causometric hypothesis because it indicates the discrete causal structure already possesses more information than what is needed to approximate relativistic geometry according to Hawking and Malamud. In more general setting, we expect that the observed system S and the observer O will be more complicated than individual elements and that the information flow between them will be represented by a large family of chains I. In this context, the distance of observation can only be defined in an average or approximate sense. An important basic question to answer in constructing such model is whether or not different chains between different elements can carry independent information. These questions play an important role in causal set theory because causal sets are defined to be transitive. For this reason, there is a direct relation between two elements whenever there is a chain between them. However, in most cases, these direct relations are not interpreted as encoding direct influence. They are merely structural byproduct of transitivity. We choose to allow direct sets that are not transitive, and we only include chains that encode actual influence. This choice is called the independence convention. It leaves no ambiguity about the meaning of individual relation. As we have stated before, it is generally preferable to carry out an observation as soon as possible after the observed events have occurred. However, in some cases, this is not possible and we must make the best of whatever data is available. This is particularly true for information about the early universe reaching us by the cosmic microwave background and similar sources. Although we are used to thinking of empty spacetime as preserving information quite well in local sense, it is entirely possible in cosmological setting for spacetime as a whole to destroy information in an irretrievable way. The most extreme example of this might be a Big Bounce type event in which information about the previous cosmological era would be forced through a cataclysmic bottleneck. In discussing ideal observation, we have so far focused entirely on what data is gathered, sampled, or intercepted, and not at all what data is actually stored, preserved, and processed. We call an observation that preserves large quantity of information about the observed system as an effective observation. Here we find it appropriate to quote Sherlock Holmes from Doyle's story A Scandal in Bohemia, in which he identifies Watson's deficiency as information processing and not information gathering. In the lower diagram, we represent the storage of information by drawing a smaller representation of S inside of O. This information storage increases the entropy of O, which gives us a quantitative means of measuring how effective the observation is. When discussing entropy in context of space-time model, it is important to distinguish between the measures of entropy associated with purely spatial object and measures of entropy associated with reason of space-time having non-trivial temporal extent. Perhaps the most important reason why this is true is because whenever we find a notion of entropy, we can expect to encounter some version of second law of thermodynamics. The type of entropy increase predicted by the second law involves purely spatial notion of entropy, because it makes no sense for a quantity to increase with time unless that quantity is associated with a particular time, that is, particular space-like section of space-time. Here again we run into problem involving anti-chain in directed sets. The most obvious analog of spatial section of relativistic space-time is the maximal anti-chain, which consists of a family of mutually unrelated elements. In the picture, we draw a dashed line connecting the elements of two anti-chains, sigma 1 and sigma 2. But this is only a visual aid to clarify which element belongs to which anti-chain. The problem is that such an anti-chain has absolutely no structure beside its number of elements, because by definition none of the elements are connected by a chain of relation. Hence, it is difficult to see how we can reasonably associate a meaningful entropy with such an anti-chain. Even if we did try to define such an entropy, the only reasonable choice would be something like log n factorial, where n represents the number of elements in the anti-chain. Increase in entropy would then merely involve larger anti-chains, and the second law would merely say space-time tends to expand. This is far too crude for our purposes. In particular, it allows no reasonable local definition of entropy increase within a space-time region of fixed size. So somehow we have to identify a subobject of discrete space-time that are essentially spatial but nevertheless possesses enough structure to allow a non-trivial definition of entropy. An excellent candidate for such a structure is anti-chain in relation space. The left-hand side of the lower diagram reproduces a picture of such an anti-chain from the previous slide. The right-hand side shows what the same structure looks like from the perspective of element space. It is easy to see how such structure can encode non-trivial entropy. We can measure the effectiveness of observation by determining how the entropy of the anti-chain changes to script R of O. On this slide, we illustrate difference between ideal observation, which samples or intercepts all the information flowing from the observed system, and effective observation, which stores or processes that information. To do this, we use a discrete causal analog of an interesting form of matter, which was only recently recognized and studied. This is time crystal, which is a structure that is periodic in time and not only in space. This idea was proposed by Frank Wilczek in 2012. Basically, by driving a special system in a certain way, we can get it to reproduce a same pattern over and over again. That means in particular that time crystal preserves no record of its history of influence from the driving mechanism, because such information would increase its entropy and allow us to distinguish early periods from the later periods. We can think of time crystal as observers and driving mechanism as an observed system. Even if we arrange for the time crystal to sample all the data flowing from the driving mechanism, which of course is unlikely on itself, it would still be completely ineffective observer because it would not store that data. It will be like Watson, seeing everything but effectively observing nothing. Now we move on to the topic of quantum observation, which is obviously more complicated than classical observation. Of course, the real universe has quantum theoretic properties, so the classical theory we have been discussing can be the whole story, just like general relativity can be the whole story as a theory of space-time structure. As we discussed on the previous slide, there are many different approaches to quantum theory, not just quantum gravity. One feature that all of these approaches incorporated was some version of superposition, in which different states are combined together to produce a quantum world. In the ordinary quantum theory, superposition is linear. The sum of two physically valid states is also a physically valid state. Some people suggested that linearity might break down in quantum gravity, but we do not really need to discuss those details. For us, it's just enough to say that we are combining many states together in some way. What are these states? Well, since gravity is about space-time structure, they are individual spacetimes. The idea is essentially same as taking sum over histories or sum over geometries, which is reasonably familiar notion in quantum gravity. Ultimately, these ideas develop out from Feynman's path integral approach to ordinary quantum theory. In the discrete causal context, what we have to do is work with configuration space of directed set, which is shown in left-hand diagram right here. Of course, we are only showing a very small part of the configuration space near the beginning of time. The blackboard bold S stands for the word scheme, which is short for kinematic scheme. The idea is that this arrangement of directed sets encode kinematics of the theory, all possible ways of that spacetime could evolve from a particular point of view without saying anything about the dynamics of what particular evolutionary process are favored. There are several different options on how we can define quantum observation from a structural perspective. One fairly slick idea is to simply treat the multidirected set script M of bold S coming from the kinematic scheme bold S the same way we treat classical directed sets. We call this higher level approach because it uses overall global structure of the kinematic scheme instead of just working with the individual directed sets. If we follow this approach, then we simply choose a subobject of script M of bold S to represent the observed system and call it calligraphic S, and to distinguish it from classical system. Notice that such a system actually represents an entire family of directed sets. We then choose a similar family for the observer and call it a calligraphic O. Finally, we choose a family of chains, calligraphic I, between S and O. These chains actually represent evolutionary pathway from directed sets represented by nodes in S to directed sets represented by nodes in O. From a structural perspective, there are methods to this madness because it simply copies what we have done classically to a higher level. However, we have to admit that this definition raises serious conceptual difficulties when we attempt to relate it to common sense ideas on what an observer or observed system should be. In particular, under this approach, quantum observer means a family of discrete spacetime that are possible evolutionary descendants of members of another family representing the observed system. It's unclear if we can make sense of this in a way that it connects it convincingly to established physics. Another possible approach to defining a quantum observation is to simply take an ensemble of directed sets out of the kinematic scheme bold S and define a classical observation in each member of this ensemble. A quantum observation then consists of all these classical observations, possibly weighed and arranged in some special way. The picture here illustrates how this is done. In the small box at the top left, we have isolated an ensemble of directed sets. Typically, we would tend to think of these sets as being somewhat similar, kind of like nearby parallel universe. For example, we might choose them all to correspond to nearby elements of an antichain in an underlying multidirected set, a script M of bold S of bold S. We then define a classical observation SIO in each of these directed sets. In this particular picture involving kinematic scheme bold S, we can only show a simple observation because number of directed set with a given number of elements n in S increases rapidly as n increases. So at the bottom we have to show a somewhat more complicated example involving directed set with about 20 elements each. If we decide to become anthropomorphic for a moment, then we can think of the red object in each of these directed sets as representing slightly different versions of ourselves in parallel universes. The ensemble approach that we discussed on the previous slide seems to make much more sense in terms of connecting it to recognizable physics than the higher level approach. So we tentatively adopt it as our definition. To be precise, we define quantum observation in configuration space, bold S, or kinematic scheme to be more formal, consist of a family of observation across a family of directed set, indexed by some index set which we call A. Now, of course, the definition leaves a lot of unanswered questions. If we ask somebody on the street what's the biggest issue with quantum observation, they would probably say something about collapse of the wave function. That is, how a superposition of state is reduced by observation process to a single definite state. Maybe we are giving general public too much credit here, but if we ask this question inside a physics building, that's probably what people would say. Now, the ensemble approach that we have outlined here does not select one of the classical observations out of the ensemble to be the one that gets actualized or randomly chosen by the observation process. Of course, what we could do is just augment our definition by adding in a probability distribution that assigns amplitude to each of our classical observations. We could then distinguish the observation itself from the result of the observation and say that the observation is weighed ensemble while the result of the observation is a particular member of ensemble selected according to the amplitude assigned by the weighing function. But we suspect that there is probably something to be gained by involving higher level multidirected structure of script M of bold S in the definition in some way. What comes to mind is something like category theoretical limit, where we have a directed system of objects, in this case directed sets, and taking the limit isolates a particular limit object. We might compare a limit object to an eigenstate chosen by an observation in ordinary quantum theory. However, the little picture we have right here on the right is probably too simple, because the structure involved is just all the evolutionary pathway leading to a directed set here at the top. So we will have to say for the moment that there is more work to be done on this topic.